Okay, so we'll be talking about null hypothesis significance testing, which I'll be calling NHST for short throughout this lecture. So we're going to talk about this before getting to statistical validity, because in talking about statistical validity, we need to talk about statistical conclusions. And the statistical conclusions we have available to us depend on which framework we're using to analyze our data. And in the framework of null hypothesis significance testing, or NHST, there are several possible conclusions. So we're always starting with the null hypothesis, which is the hypothesis that there is no effect. There's no correlation between my variables or no difference between groups. And we might reject the null hypothesis, conclude that the null hypothesis is false. So there we're concluding there is something here, there is an effect. My two variables are correlated or my groups are different. Another possible conclusion is that there is nothing there. The null hypothesis is true. And finally, a third possible conclusion is that we can't tell whether or not there's something there. We can't tell if the null hypothesis is true or not. So these are three possible conclusions from null hypothesis significance testing, and we'll come back to them in a minute. So the fact that these are the conclusions available to us means that there are two different kinds of errors we might make. One is a false positive error. In null hypothesis significance testing, it's called a type 1 error. And it's when you think you see something there, but actually there's nothing there. So you reject the null hypothesis, you think the null hypothesis is wrong, there is something going on, but actually you're wrong. The other kind of error, a false negative error, is called a type 2 error in NHST. And this is when you think there's nothing there, you fail to reject the null hypothesis or you even accept it, but actually there is something there. So you can tell I'm already blurring the line between two of the possible conclusions, accepting the null hypothesis, saying there's nothing there, versus failing to reject it, saying I can't tell if there's something there or not. I'm going to blur those two together for now, partly to simplify things and partly because it's often what researchers themselves do. And so that leads to the potential for false negative error, even when all you're saying is I don't know if there's something there, I failed to reject the null. You might actually be making a false negative because you might be tempted to overinterpret that as that must mean there's nothing there. And then you're vulnerable to a false negative error if actually there is something there. All right, let's simplify this a bit. So let's make a table where each row is going to be our conclusion after collecting data, analyzing it, and getting a statistical result. So after we do all that, we may end up in the top row. So we fail to reject the null. We say, it's possible there's nothing there. I wasn't able to reject that null hypothesis. That's if we get a non-significant result. Or the other possibility after we analyze our data is that we get a statistically significant result with a p-value less than 0.05. We'll come back to what that means. And in that case, we reject the null hypothesis. We say, I think there is something there. I think the null hypothesis is wrong. Hopefully this is familiar to you. So we're going to cross that with two columns, which I'm calling the true state of the world. So we either live in the left column or we live in the right column, and we don't know which. So we know which row we end up in after we run our study and analyze our data, but we never know which column we live in. It's possible that we live in the left column where the null hypothesis is true, there is no effect, or we live in the right column where the null hypothesis is false, there is an effect. So I'm going to stretch that a bit and say that the research hypothesis is true, which I'll call H1 here. So if we cross those two rows with these two columns, we get four possible outcomes. So the correct conclusions would be, if we live in the left world where the null hypothesis is true, the correct conclusion is there is no effect. So the best case in the case of NHST is we fail to reject the null. And when we live in the right world where the null hypothesis is false, there is something there, then the correct conclusion would be a significant result. We conclude that we reject the null, there is something there, that would be the correct conclusion. However, as I mentioned, we never know which column we live in, we only know which row we end up in. So when we end up in the top row, maybe that's a true negative. Maybe we didn't detect anything because there's nothing there. We live in the left world. But the other possibility is that we live in the right column, and that was actually a false negative error. We weren't able to detect something. We weren't able to reject the null, but actually we should have if we were accurate. And then when we land in the bottom row, we get a statistically significant result. One possibility is that it's a true positive, that we live in the world where there really is something there. But the other possibility is that we live in the left world where the null hypothesis is true, and this was a false positive. We thought we detected something, we rejected the null, but actually that's the wrong answer. So if we had this all-knowing view of the world, we could know when we're making a false positive or false negative error, But as it stands, as mere humans, we can't know that. We just know which error we're at risk of making. So if we're in the top row, we're at risk of making a false negative error. If we land in the bottom row, we're at risk of making a false positive error. So before we go further, I'm going to dig a little deeper into what a p-value is. So p less than 0.05 is our threshold for statistical significance in psychology and in many other fields. And I'm sure you've heard of a p-value before, but it's actually something that's quite difficult to define. So I'm going to attempt to do that here. And it's a useful thing to learn to spot because it's misused very, very often. So a good part of statistical validity is having a strong grasp of the meaning of a p-value and being able to detect when it's misused by other researchers. So in NHST, we start by assuming that the null hypothesis is true, but actually we don't really believe this. Most researchers don't believe that the null hypothesis is true. They have their own research hypothesis, which is not null. So their research hypothesis is that there is a correlation, there is a difference between groups, there is an effect, and they want to reject the null hypothesis. But to do that statistically, we have to start with the assumption that the null hypothesis is true in NHST. And then we ask, how likely or unlikely is my observed result that I got in my study that I ran if I assume that the null hypothesis is true? So we get a probability of how likely would this result have been if the null hypothesis was true. So we're asking, is it likely enough that maybe it was just a fluke? So sampling error is kind of another name for fluke or random error. It's a kind of random error. So I'm going to illustrate what sampling error is in the next slide, starting with the assumption that the null hypothesis is true. So if we live in a world where the null hypothesis is true, there is no effect, no correlation, no difference between groups, so the true effect size is 0, and we run a study, we should get an effect size close to 0 most of the time, right? Most of the time, if I flip a fair coin, I'm going to get about as many heads as tails. I hope that works in Australia. I'm not sure how coins are referred to, the two sides of a coin are referred to in Australia. So typically my effect, it might not be exactly 0, but it'll be close to 0. Now, let's say I run my study over and over again, and I'm going to plot the distribution of results over all the instantiations of the study. So I run the study once, I get an effect of 0. I run it again, maybe the second time, I don't get exactly 0. Sometimes I get a result very positive or very negative. So those would be flukes. This is when actually the true effect is 0 every time, but just because of random error or sampling error, I'm sometimes getting an effect in the positive direction, sometimes in the negative direction. And once in a while, even just by chance, when the true effect is 0, I'll get an effect quite far from 0. So this extreme effect would have the smallest p-value, because the p-value tells you the probability of getting this effect you observed in your one study under this null distribution. When the null hypothesis is true, you can know the shape of the distribution of what results you would get if you ran your study over and over again. It would be a normal distribution centered around 0. So this is called the sampling distribution of the null hypothesis. And you compare your actual results. So let's say I get a result that's a positive result, bigger than 0. I can look at what's the probability of getting a result at least this extreme under the null hypothesis, if it's just chance. So the idea would be like if I'm flipping a coin, my null hypothesis is that it's a fair coin, that there's no difference between the chances of getting a heads or a tails. I flip it 10 times and I get 8 heads. And I think, oh, what's the probability of getting 8 heads instead of 5 out of 10 if actually it is a fair coin? Sometimes that'll happen just by chance. I can calculate that probability. Same logic here. You calculate the probability of any result at least that extreme. So notice I'm not saying the probability of that exact result, but a result that extreme or more extreme. And to get that probability, I have to look at both extremes. So a result as big in the positive direction or negative direction. And that probability is just the amount of area under the curve that's at the point of my observed result or more extreme in either direction. And that's just what the p-value is. It's the proportion of area under the curve of the null distribution, the results you would get if you ran a study over and over again when actually the null hypothesis is true, that's as extreme or more extreme than my result that I am calculating a p-value for. So a p-value tells you if the null hypothesis is true, what is the probability that I would get a result at least as extreme as the one I got? So the smaller the p-value, the more extreme the result, or rather the more extreme the result, the smaller the p-value. And we've decided in many fields, including psychology, that if that probability is less than 5%, 0.05 corresponds to 5%, we're going to say, okay, the null hypothesis isn't true then. This is such an unlikely result if the null hypothesis were true that we're going to reject the null hypothesis. But it's really important to point out that this is not really sound logic. Just because something is unlikely if the null hypothesis were true doesn't mean that the null hypothesis is unlikely to be true. We're just going to have to accept for now that a fundamental part of NHST is this kind of twisted logic of I'm going to calculate how unlikely this is under the null. If it's really unlikely, I'm going to reject the null, even though that's strictly speaking not logically sound. So here's another way to think about it, another figure illustrating the null distribution. So again, this is a distribution centered around 0 of what the spread of results would look like if we ran the study over and over again. Most of the time, the results would be close to 0, but sometimes just by chance, we would get extreme results in the positive or negative direction. A lot of heads or a lot of tails. So alpha is the critical p-value, what p has to be less than in order to be considered statistically significant. So we compare p to alpha. If p is less than alpha, we call it statistically significant. So we're going to take the 5% most extreme results under the null. If we get something that extreme, we're going to reject the null hypothesis. In psychology and many other fields, we use an alpha of 0.05. So this concept of alpha is going to come up again. It's just what p needs to be less than in order to declare that something is statistically significant. How unlikely an effect has to be for us to be prepared to reject the null. In psychology, we typically choose 5%. Okay, so if we go back to this table, what we're saying is that when we live in this left world where the null hypothesis is true, we're prepared to make a false positive error 5% of the time. We're going to accept that when the null is true, just by chance, we're going to get an extreme result 5% of the time. We're going to reject the null, but actually that was the wrong decision because we don't know that we're living in the left world. But by adopting this convention that alpha is 5%, we're accepting that when we live in this left world, we're going to make a false positive error 5% of the time. That means that the other 95% of the time when we're in this left world, we're going to correctly think that there's nothing there. We're going to correctly conclude that we didn't observe an effect. We can't reject the null. Now the right side of the table, when the null is not true, also has some percentages assigned to the two possibilities, false negative or true positive. But those aren't fixed the way that alpha is. So alpha, we just accept 5%. That's what the rule we're going to go with in all of our research, barring some controversy at the margins. But on the right side, there is no fixed percentage about what are the chances of a false negative when there really is an effect. So we call that top percentage beta, but it's not fixed at any particular level. And the flip of that, the inverse of that, the chances of a true positive when there really is an effect, the chance of detecting something when there's really something there would be 1 minus beta, because beta is the probability of missing the effect. 1 minus beta is the rest of that probability of detecting the effect, and we call that statistical power. So statistical power is your chance of detecting an effect when there really is an effect there. Statistical power is only relevant when we live in the right world, where there really is an effect to detect, and it's just 1 minus the rate of false negatives. So in NHST, the process is we run a study, we analyze our data, we get a p-value, which is the probability of a result at least that extreme under the null. We compare it to alpha, the critical p-value, which in psychology is usually 0.05. If it's significant, we reject the null hypothesis. And this gives us some reassurance because if we follow all the rules of null hypothesis significance testing, over the long run, we can rest assured that when we're in that left world where the null hypothesis is true, when there is no effect, we'll accidentally reject the null hypothesis, we'll get a false positive alpha % of the time. And we're okay with that being 5% of the time, we know we're going to make a false positive. We won't know which times those are, when that's happening, but we know that over the long run, of all the times when the null hypothesis is true, we're only going to accidentally reject it 5% of the time. And then on the right side, when we live in the right world where there really is an effect, we'll accidentally miss it, get a false negative beta % of the time. And we don't fix beta to a specific number, but we can control it by controlling our statistical power. And we'll talk about how we do that in following lectures. So this error control is one of the nice features of NHST, that we can control the risk we're willing to take that we're going to make a false positive or a false negative error. The false positives are controlled by alpha, the false negatives are controlled by beta, or inversely by statistical power. But all of this is only true if we follow the rules of null hypothesis significance testing, and very often we fudge these rules a bit. We're going to get into that when we talk about statistical validity. So actually, as practiced, it's not always the case that we can rest assured that our probability of false positive or false negative errors are controlled in this way. And then I'll end with one more point, which is that I talked about these three possible conclusions, but actually, strictly speaking in NHST, we should never conclude that the null is true. Our only options really are to reject the null if we detect an effect that's unlikely enough under the null, or to fail to reject the null, which we should just say we don't know if there's something there or not. We weren't able to reject the null. In practice, that often gets blurred into accepting the null, saying, well, I didn't detect anything, so there must not be anything there. But technically, that's not allowed under NHST. You would have to use a different approach if you wanted to have the chance of coming to the conclusion that there's nothing there. And there are other statistical approaches besides NHST, but we won't get into them here.